First lesson in Chapter 6 involves rate of change, and it comes immediately following a section that we had on dividing in algebra and ratios. We're going to look at some different ways to calculate rate of change, which is going to involve subtraction within one ratio. So the big idea is that the rate at which a quantity changes can be determined either by computation or by looking at a graph. So both are acceptable. We'll be doing computation in addition to looking at graphs for determining what the rate of change is in a certain situation. There's two vocabulary terms, rate of change and rate unit, that we will be defining. So what is rate of change? Let's consider the birth of a baby girl. The girl's name is Joy, weighed 7.5 pounds at birth. At the end of 4 months, the baby weighed 13.5 pounds. The question is, how fast did her weight change from birth to 4 months? Now, to answer this question, we calculate the rate of change of Joy's weight, that is how much she gained per month. So if you look at what's in the red box there, from 0 to 4 months, change in weight was 13.5 minus 7.5. So that's a difference of 6. So we're going to write 6 on that line. And how many months went by? 4 minus 0 is 4. Now, at this point, this ratio represents 6 pounds per 4 months. What we always want to do is calculate per 1 month. So when we divide that, we get 1.5 pounds per month. So that would be the correct way to represent the final answer. So you don't want to leave it as 6 over 4. You want to leave it as the division, which is 1.5, so it's per 1 month. Rate of change is per 1 unit. So that's A. Now, the question that comes next, 2B, what ratio compares change in weight to change in age from 4 to 6? We're going to do the exact same thing. Now, at the bottom of this slide, it says at age 6 months, Joy weighed 15.75 pounds. How fast did she grow from 4 to 6? We're going to use the same method. So we have 15.75 minus 13.5, and that gives us a change of 2.25. And in this case, only 2 months went by, and so we have 1.125, and then I'm going to also write pounds per month. So again, we don't want to leave it as 2.25 divided by 2. We want to leave it as 1.125 pounds per month. Now the question in 2C is asking which time period had faster rate of change. Well, you can see from the information out of the book, 1.5 is greater than 1.125, and so we know that the first time period was faster from 0 to 4. That's the faster time period. Now, is this what you would expect? If you consider a newborn baby, they grow very quickly in the first few months. They continue to grow quickly, but the rate of change goes down. Now the difference between these two numbers is 1.5 and 1.125. So really only 4/10 difference. But the answer here is yes, and that's because newborn babies grow at fast rates. So that would be what we expect. Now the definition for 2E is right here on the slide. The rate of change measures how fast the graph goes up or down when reading from left to right. So you could also look at the graph and say, well, the line from 0 to 4 is steeper than the line from 4 to 6. That also proves that it's a higher rate of change. We can tell also from looking at the number. And that was the big idea. You can either compute or you can look at a line graph. In this case, we did both, but we computed the two rates of change from 0 to 4 is steeper, or a larger number, than from 4 to 6. So let's take a look at example 1, which says the population of Chicago from 1830 to 2000 is shown in the table on 325. So I need to gather some information from the book on 325, so make sure you turn there. We're going to calculate it in terms of people per year, so we don't want to have it per 10 years or per 20 years or whatever, per 1 year. The first question is from 1890 to 1900. So let's take a look at our data here. Make this larger, and let's see if we can figure this out. Here's our table. You have your book there. We have to find the numbers for 1890. The number right there is 1,099,850. So I'm going to write that down. I'm going to do it on the side here. You can do the same thing. 1,099,850 minus, and now we're going to look at the value for 1900, which is 1,698,575. That has to be the numerator, because it says people per year. So the people has to be on the top. So I'm subtracting to find the difference. Now the denominator is then years. And I'm just going to take 1890 minus 1900. And now I'm going to calculate this difference. So I'm going to take 1,099,850 minus 1,698,575, and I get this number right here. Negative 598,725. So I'm going to put that right here. Negative 598,725 divided by, this is clearly going to be negative 10. So I'm going to take this answer, I'm going to divide it by negative 10. My answer is going to be positive. The change is then 59,872.5, and then I'm going to put people per year. And that's my final answer for 3A, 59,872.5 people per year. That's the average rate of change from 1890 to 1900. I'm going to do the same thing. Oh, by the way, before we go on to 3B, I could have switched this around and gotten the exact same answer. So if I did 1,698,575 minus 1,099,850, I'd have to do in the bottom 1900 minus 1890. The order actually doesn't matter as long as you're consistent. So these numbers right here have to be year and population match, and these have to be a year and population match. The order doesn't matter. Either way, you're going to get the same answer. So in 3B, we look at our data, and from in 1970, 3,369,357 minus the 1980 data, which is 3,005,072. My denominator is the same, 1970 minus 1980. So I'm going to calculate, like I did with 3A, 3,369,357 minus 3,05072, and that gives me 364,285 divided by negative 10. So what's going to happen here is, because the denominator is still negative 10 from 70 to 1980, when I divide this, I'm going to get a negative rate of change. So this answer is negative 36,428.5 people per year. Alright, so rate of change can be positive like in 3A, it can be negative like in 3B. Alright, so now for number 4, it says rate of change, and that's going to be what I have in the red box. The rate of change between x1, y1, and x2, y2 is always the difference of the y's divided by the difference of the x's. Okay, so all the 1's and the 2's represent is your first x-coordinate, your second x-coordinate, your first y-coordinate, your second y-coordinate. For example, when I had the first problem with the births, or the birth of Joy, you could think of this as 2 ordered pairs. 0, which corresponds with 7.5, and then 4 corresponds with 13.5, right? So if you thought of the birth of the baby this way, you'd have x1, x2, y1, y2. And so if you look at what you did for 2a, you did the exact same thing. 13.5 minus 7.5, so y2 minus y1, divided by 4 minus 0, which is the x2 minus the x1. All these represent are the different x and y coordinates. The key is that they have to be consistent. Okay, you start with y2, you got to start with x2. And then you'll get your rate of change. So then what you want to put on this line for number 4 is the definition for rate of change. You have 2 ordered pairs, so y2 minus y1 divided by x2 minus x1. So what you can go ahead and do is look at number 5 and calculate the 2 rates of change. I'm not going to show the work here, but you can calculate the rates of change from 99 to 2000 and from 2001 to 2002. And you would use the data in the chart. So go ahead and give that a try and see what numbers you get in, and as you see underlined, people per year. So when you're finished with that example, take a look at example 2, which can be a 0 rate of change. It shows attendance at baseball games that went into extra innings. So see if you can answer 6A and 6B. During what interval did the attendance not change? So what time periods from what to what? And then 3B, find the rate of change of attendance during that time. So what was the rate of change? What number represents that time period that you found in A? And then we'll check those as well. Once you're finished with that, the last thing here just gives a nice little summary of the different rates of change. If you have a positive rate of change, it's going to be an upward slant line. You can see what the graph looks like. Constant decrease is negative, and it would be a downward slanted line. No change is going to be 0 as the rate of change, and it's got to be a horizontal line because there's no change left to right. That helps understand positive, negative, and 0 rates of change.